Here I have a plant cell, and I don't know what the osmolarity of the cytoplasm is exactly, but let's just assume that it's 0.45 osmoles. Again, I don't know, but this is going to help me begin to make sense of my data, because what I do know is that I'm placing the plant cell in solutions of increasing osmolarity. We're looking at sucrose solutions, so this is the molar concentration, which also happens to be equal to the osmolarity, because if you remember, to convert molarity to osmolarity, we're going to take I and multiply it by C. For sucrose, I is 1. So each of these numbers represents the value of C, the molar concentration. So I'm just multiplying these numbers by 1, and I get my osmolarity. So let's think about what the cell is going to do in these environments. If I place the cell in a 0 osmolar liquid, that's just basically pure water, no solutes. Water always moves to the hypertonic side. So in this case, water is going to diffuse into the cell. So I would expect the cell to gain mass. If I place it in a 0.2 osmolar solution of sucrose, I would expect the cell to gain mass. Because again, the water is going to diffuse into the hypertonic solution. The hypertonic solution is the solution with the greater osmolarity. If you think about it from the water's perspective, the concentration of water, of free water, excuse me, is high on the outside. The concentration of free water in the cytoplasm is low because solutes lower the amount of free water. How much water will go into the cell in this scenario, 0 molar, versus this scenario, 0.2 molar? I would expect more water to diffuse into the potato cell or the plant cell if it's surrounded by pure water, because the concentration gradient, the difference in the free water concentration, is more extreme in a 0 osmolar solution. And we know that the concentration gradient affects the rate of diffusion. You can think of the concentration gradient as the angle of a slope. So if I have a ball and it's going to roll down this slope, the ball is going to roll down more quickly in this scenario. Here's scenario A, here's scenario B. It's going to roll down, it's going to reach the bottom more quickly in scenario B. This slope represents, the angle of this slope represents the difference in concentration. So the difference is more extreme in a 0 osmolar compared to a 0.45 than a 0.2 compared to a 0.45. So if these plant cells are sitting in a beaker for a day, then I would expect to come back the next day and see a gain in mass in 0 and 0.2 and even 0.4. Because if I expose this cell to a solution that has an osmolarity of 0.4, again, water is going to move to the hypertonic side, but the rate of diffusion is going to be relatively slower because the concentration gradient is not as extreme. Now in 0.6, I would expect the plant cell to begin losing water because now the exterior solution is hypertonic. And again, water moves to the hypertonic side, so I would expect the cell to lose water. Now the difference in osmolarity is about 0.15 osmoles. If I change that from 0.6 to 0.8, the difference becomes more extreme. Now the difference is 0.35 osmoles. So it's a more extreme difference. The concentration gradient is more extreme. I would expect the plant cell to lose even more water relative to when the solution was 0.6. And then finally, if I have the plant cell in a 1.0 osmolar solution, I would expect it to lose the most amount of water of all of my choices, because here again the gradient is the most extreme. So I'm going to pause it and set up my graph, and we're going to try to make sense of the data. Okay, so I've unpaused it. I've also given a letter to each solution. So let's imagine for a second that we actually don't know all of my osmolarities. All I know is that I have solutions L, M, N, O, P, Q. And what I can do is I can say, okay, in solution O, I gain the most amount of water, and then I gain the second most amount of water in solution N, and then I gained a little bit of water in solution L. I lost some water in Q. I lost a little bit more water in M, and I lost the most amount of water in P. So now I can take that information and say, okay, well, of all of my possible choices, I'm going to assign O as the 0 molar solution, and I'm going to assign N as the 0.2, L is the 0.4, Q is the 0.6, M is the 0.8, and P is the 1 molar solution. Again, that's just based off of the logic that we established at the beginning of the video. And now I'm going to graph the percent change in mass. So I don't have the actual numbers, but let's say the percent change in mass, and again, I'm not going to graph it as LMNOPQ. I'm going to graph it on my x-axis as the osmolarity choices. So I'm going to say that for 0 osmolarity, I'm going to assume that that was beaker O, and let's say that my percent change of mass for beaker O came out to, I don't know, like 22%. And then I have my 2 SEM, so I'm going to create my confidence intervals so I get something like this. 0.2, that would be whatever my percent change in mass is for beaker N. So it was positive. It was a little bit less positive, but it was still positive, and so I have my 2 SEM. For 0.4, let's say it was barely positive. Well, let's make it something like this. There's my 2 SEM. 0.6, maybe something like this. 0.8, something like this, and 0.1, something like this. Okay? Now, I want to mention something important. Notice that, and I did this on purpose, I intentionally made it so that we see overlap here. So what that means is that I don't have enough information to argue which letter is 0.8 and which letter is 1. So for example, if you wanted to argue that P had an osmolarity of 1, someone else could just as easily argue, no, M had an osmolarity of 1. And the reason is because since the confidence intervals overlap, we can't be sure which sample average is truly higher. So the sample average that we got, the sample average that we got had a more negative change in mass for P and a less negative change in mass for M. But because the confidence intervals overlap, it's very possible that the true average for M, which is this guy right here, it's possible that the true average for M is all the way down here. And it's possible that the true average for P is all the way up here, right? And so if the orange dots represent the true averages, then the scenario would actually be flip-flopped. We would actually conclude that M is 1 molar and P is 0.8 molar. But we just don't know. We can still be confident in stating that M and P were the most hypertonic out of all of our possible choices. But nailing down the exact osmolarity of M and P can't be done with this data set. It doesn't mean that our data is invalid. It doesn't even necessarily mean that we did something wrong. This could be due to sampling error. It could be due to mechanisms that are happening inside of the cell where it's trying to minimize water loss. It could be that 0.8 and 1 cause the cell to lose as much water as possible, and so increasing the osmolarity past 0.8 isn't going to make a difference because water is already leaving as fast as it can at an osmolarity of 0.8. So the point is that there's many reasons why the data might be the way it is. I don't want you to think that just because confidence intervals overlap, then suddenly our data is garbage. That's never the case. But just be aware of what you can and cannot conclude when you do see these overlapping intervals.